matched the matched window, and this is called the moving window that we mentioned last time. So you move it 1 pixel by 1 pixel, and then try to find out where is the matched conjugate point. But however, like we mentioned last time, it will be very time consuming because you will go over a whole image to find one specific conjugate point. And also, you have large chance to find the wrong match because maybe there's another patch or another window somewhere that have high correlation with this target window, and then you find you will treat it, that one as the match point. But well, you will find out, okay, so that is a wrong match, and then in this case, when you perform the space intersection, then either it could not give you a solution, or it cannot give you one good result. For example, it will give you one wrong answer. So basically, that's the case. So so in this case, we want to like limit where the moving window like moves. So traditionally, we will have different ways then try to estimate where should we look at. And normally, we will create, for example, a search window somewhere. And this is the search window. Right. And we will put the moving window inside the search window. Right. We will put the moving window inside the search window and then move it pixel by pixel and try to find out where that is. So the estimation of the of the search window becomes important because that matters to, for example, the performance, and also matters to the accuracy as well. So that's pretty much about the very general and very basic idea of what image matching is. So you have target window and you have a moving window, and then just move it and then compare the similarity between the target window and the moving window. And normally we will have different ways to calculate the similarity. One traditional way, but also actually very widely used calculation is called NCC. The one is what that is usually used is the NCC, normalized cross correlation. So maybe you guys have see these before. Basically, when you are comparing two like image patches, and then you want to determine whether it's similar or not, then this is a very common way to determine that. So and basically, it's very easy. Actually, on the if you take a look at the slides, then there's an equation for that. I'm not going to basically okay. Basically, what the NCC does is actually calculating if you treat these two windows as because in a hyper-dimensional domain, for example, like let's just say one specific domain. One specific, you can say space. Then in this case, one window represents one vector. Okay. So let's just say it's the target. Right? This is the target window vector. If you treat each of the pixel as one dimension, or if you treat each of the pixel as one dimension, then in this case you have a hyper-dimensional space. And in this case, one window represents one vector in that space. And of course, your moving window will represent the other, you can say vector. So that's just a moving. So what the NCC is calculating is actually this one. It is calculating the cosine theta. Right. It's actually calculating the cosine theta. Okay. So basically, that's what the NCC equation. If you take a look at the NCC equation, then that's basically what it's trying to calculate. Okay. So as you can imagine, if if the two windows they are exactly the same or very similar to each other, and the theta angle, the theta angle will be very small. And if you have a very small angle over here, and then NCC value will become closer to and closer to 1. It will be closer to and closer to 1. So in this case, it will be like, usually when you calculate the NCC value, then if you are starting from, let's say, usually it's more larger than 0 and to 1. So if it's closer to 1, then that means these two windows, they are very similar. They are very similar. So then you can determine, say, okay, so this is a very highly similar windows. Okay? And however, you may also wonder, for example, if right now you are doing, you are working on this, and then what exactly is the threshold that we will set, we normally set, to determine whether the two windows are similar or not. So usually, for the threshold, we will use, for example, like 0.7 to threshold. Usually 0.7 to 0.9. The threshold usually is from 0.7 to 0.9. Determining on, depending on the content that you have on the image, right? Depending on the content that you have on the image. Okay, so that's pretty much like that's pretty much about the case. And then this is the most widely used or most commonly known solution to perform the image matching. So basically, what you can do is you have the target window and you have a search window, and then you move your moving window inside the search window. And every time when you move, then you will calculate the NCC coefficient, the normalized cross correlation coefficient. And then if the correlation is closer to 1, then which means that these two are similar. But however, if you want to determine how similar it is, or it is similar enough, then usually the threshold that we set is from 0.7 to 0.9. Okay, so before we move on to other things, then let me ask you guys a question that I might just give you guys a preview. So earlier when I asked to determine the size of the target window, it depends on what type of factors, what are the factors that will affect the size of the target window that you open. And that may also influence the same factor. That may also influence the threshold that you decide over here. The threshold that you decide to identify or to determine whether these two windows are similar or not. So what is the factor that decide that, or what are the factors that could affect the decision of the size of the target window? Right, think about this. So, what do you think?
Maybe illumination.
What do you mean by illumination?
The energy received will affect the gradient.
So
the pixel of the window will be affected by the range of the gray blue.
So in this case, you mean if there's a lot of energy that you will have a larger or smaller window? Is that what you're trying to say?
That kind of concept.
So larger energy, then how would you decide? Is a larger window or a smaller window?
I guess it's smaller.
Why?
Why? Because we want to classify the little difference between the pixels, so we need a small moving window to determine
But if you have a larger window, what's the harm of that?
What's the harm?
Yeah. Does it do any damage on that? If you have a larger window and you have a larger, enough energy, and is there any difficulty on that?
Maybe the little difference could be refused or cancelled by the average size of.
Okay, I don't understand about what you're trying to say, actually. Queen?
I think it depends on your grid size.
The grid size? The grid size of the resolution of the image? Is that what you're trying to say? Yeah, you actually talk about one thing. Let's say earlier, I actually kind of intentionally didn't mention one procedure. So the whole procedure over here actually is under one assumption, which is the resolution of these two images. They are similar, right? They are similar. For example, they are all, for example, like 20 centimeter resolution, and then you can directly create, for example, like if you create 7 by 7 window over here, then you can also create a 7 by 7 window over there. But however, usually the resolution of the two images, they will be a little bit different, and also maybe a lot different because of you have different flight height, or even they are from different camera or from different system. Then in this case, if their resolution are different, then you need to normalize that first, or you need to normalize that first. And how to normalize that? Well, you can kind of, it's a little bit advanced, it's like I said, it's a little bit advanced. What you can do is actually you can perform some sort of fake auto rectification, right? Some sort of fake auto rectification. So what do I mean by that? Actually, you can imagine if right now this one is, for example, it's a tilt photo. Let's say it's a tilt photo, and then it's a closer. You take the image over here, for example, and then in this case, you cannot directly use two raw image and then to compare that, because one it has the tilt angle and one has a vertical angle, and then if you just open the same, for example, like 7 by 7 window, and then and just cut it off and then try to calculate the NCC correlation, then they will be wrong because their projection are totally different, and resolution are also totally different. So what you probably need to do first is to normalize it to a certain, for example, to both as the vertical photo and with the same resolution. So how to do it? The idea is maybe you can set a certain, maybe what you can do is you can set a certain elevation. You can set a certain elevation, and then you can project this image to this elevation. You just directly treat this elevation as the terrain, and then you perform the auto rectification for the master image and also for the self image. So in this case, originally maybe the self image is a tilt photo, but however, after you perform the auto rectification, it will be a vertical photo, like that. It will be a vertical photo, and with the same you can say resolution that you set for the auto image, the auto image. So in this case, these two images that originally may have different tilt angle and also may have different resolution, they can be unified. Okay, they can be unified, and then in this case, you have the same resolution, and which indicates the same scale of image, and then you can try to find the conjugate point by using the procedure that I previously mentioned, which is, for example, 7 by 7 and 7 by 7. This 7 by 7 coverage, it will be exactly the same as the 7 by 7 coverage on the slave image. Okay? Okay. Did I lose you guys? Did I lose you guys? A little bit? Yeah, a little bit. Okay, sure. Okay, let's assume. You have one photo over here, and then you have another photo over here, and And these two photos, you want to find these two conjugate points. But however, the current problem is their scale, the image scale, the photo scale of these two are different. And also, you can say their projection are also different. One is the vertical photo, and the other one is the tilt photo. So in this case, the easy procedure of finding the conjugate point is you find the target window over here on the master image. But right now, if you create, for example, like n by n window, if you also create an n by n window over here, n by n window, this n by n and this n by n, they actually cover different size of the region because their resolution are different. Right? Because as you can see, slave image is closer to the ground, so the resolution is higher. So it covers maybe just half of the region of the target window. So how can you directly calculate their similarity? Because they have different scale. For example, one could actually cover this region, and the other one could only cover this region. Even though they have the same n by n. Right. Even though they have the same image size, they are both n by n. However, in reality, they cover different region. So you couldn't directly use the NCC to calculate that, okay? Because the resolution, the image scale, they are different. So you need to normalize that so that you can calculate the